In our model of projectile motion, the horizontal and vertical motions decouple. The horizontal motion is motion with constant speed, and the vertical motion is motion with constant acceleration. This is an approximation, which neglects air resistance. It's pretty good in a number of settings, but keep in mind it is a model. This model is kind of fun because it connects two of the scenarios that we've been working on so far. The most classic projectile motion problem is just launching a projectile on level ground. It's like one of those video games. We have a little turret that fires little rockets at other turrets. So in that video game, usually what you specify is the launch angle and the launch speed. And the classic thing you want to know in that video game is how far the projectile goes because you want to hit your enemy. Right? But there are lots of other settings. You're playing football, you kick the football, and you want to know how long the football stays in the air to know how far you can advance down the field. Or maybe you're a figure skater and you launch into a jump and you need to know how many rotations you're able to make, which usually to how long you're in the air. So let's start with a classic problem here, which is just understanding what is the shape of this trajectory. And to understand that shape, we write down the equations of motion for the horizontal and vertical components. Now, when I write something like this, I always have to remember that I have some axes and some origins that are chosen. So I have the x direction is pointing in that direction, for example, and the y direction is up. And it's because I chose the y direction up that this is acting, is that this is the negative sign. Okay. Now, of course, one nice thing here is I could always choose my origin so it sits at the launch point. If I do that, my initial positions drop out. I'm going to do that because that's going to simplify our equations. It's not always the best approach, but it's often a good approach. And this is an example of a more general feature in problem solving in physics, is that often you get to make arbitrary choices, and how you make those arbitrary choices can make your life either harder or easier. All right, so now if I want to know what this trajectory is, I don't care about time. So I want to eliminate time from these equations. And there's an easy way to do that, which is I look at this first equation, I just solve it for time. And then I can substitute that equation into this one. So this term is here, this term is there. All right. Well, the wonderful thing about this is, there's weird constants floating around, but this is a parabola. And so we know that the trajectory is always going to be a parabola. Now you might ask, did my choice of where the origin was affect the shape? No, that's just shifting the parabola about. So we're always going to have a parabola. Okay, so let's see what else we can figure out. Let's restrict to the flat case. And let's draw our trajectory. And there's a few questions we could ask. We would ask how high it goes or how far it goes. let's ask how far it goes. Okay. Now, if you're not used to doing these problems, that may be a difficult question. And one of the problems is just how do you formulate that? And really the trick is figuring out what is the mathematical description of this endpoint. How do you determine when you get there? Right? And in this case, the answer is that endpoint is where y equals 0. So to find how far this projectile goes, I take our equation for the trajectory and I just find out where y equals 0. Now, this is a quadratic equation, but we don't need any fancy quadratic formula to solve it. All we need to do is just factor out an x. All right, you may ask, how did I know that factoring that out was the right thing to do? And it doesn't really matter. All you're trying to do is just solve this equation. So another way you could solve it is you pull this thing over to that side. And then you're going to realize that there's two solutions. One solution is when x equals 0. The other solution is when this term equals 0. Now, why should there be two solutions? Oh, there's two places where this parabola hits the ground. It hits the ground at our launch point. It hits the ground at a distance d. So that means that this is how far projectile flies. If I make the initial x velocity higher, it goes farther. Right? That's because it's moving faster in that direction. If I make the initial y velocity higher, it also goes farther. And that's because it spends more time in the air. So if you think about the initial premise that the horizontal and vertical motion separate, the amount of time it spends in the air is completely determined by the y motion. And so larger Vy, larger time in the air, larger distance. Okay, so another thing is, so this is kind of a cool result. All right. Is this an equation you want to memorize? And I would say no. So this reasoning isn't so hard, and we're probably not going to give this particular problem on an exam. We'll probably give you something else, right? Now, so for the exams and the quizzes, you're going to be allowed to bring in a concept sheet. That's going to be a sheet where you write down, what you feel are the important concepts. And this might belong on the concept sheet. But if you put it there, make sure to say when it is good. So this is for knowing the conditions under which a particular model applies is as important or even more important than the formulae which mathematically describe that model. Okay, so these projectile motion problems can get tricky. So one thing I did to aid you in thinking about them is I made what I refer to as a concept sheet, exactly like the sort of thing you can bring with you to your exams, except this one is just focused on this one concept. And it lists sort of what I think I need to remember. All right. So I wrote on it that projectile motion, there's gravity, no air resistance, no other forces. And here's a typical launch scenario. One thing you often are given is as in those little video games, is you're given the magnitude of the velocity and angle. So I think it's useful to write down all the trig there. And there are also a couple different geometries of problems they can give you. They can give you this flat ground one, which we just thought about. They can give you, say, launching a projectile off a cliff. You could have actually some uneven ground. You could, actually in those video games, you tend to have that. Or here's a little weird one. You could, be shooting a bullet at a wall. Right? In all cases, these are parts of a parabola. And then in order to actually solve the problem, the concept is that horizontal and vertical motion decouple. And I wrote down the equations of that the horizontal and vertical motion are described, and the little graphs of what the position, velocity, and acceleration look like for those cases. Right? These graphs are really useful. Then to further help you, I also have a template which it's just a big blank sheet of paper. And on the side, it has the sort of condensed version of what I had in that concept sheet, and then a space to work problems. Right? And this is really useful because then you have all the equations you need sitting right there. You have a little graph. Often, if it's not this particular scenario, you might have to draw your own little picture. But it gets you thinking, gets you remembering where this all sits. All right. So there are links to both this template sheet for problem solving and this concept sheet on in the transcript to this video.